Our third presentation will turn to solar thermal technology and will be done by Raquel Diaz. Dr. Diaz is the Director of Technology Strategy of Abengoa, a world-leading company in this solar thermal technology. So Anna, the floor is yours.
Thank you. Ladies and gentlemen, what you see here is the biggest solar thermal electrical power plant in the world. It has 280 megawatt and 6 hours of storage. This storage means that we can provide electricity after the sunset, during the night, and also early in the morning. This solar plant is green, is sustainable, is dispatchable, because we use storage in order to be dispatchable, in order to adapt to the demand, but also is affordable. This solar plant, the technology inside this solar plant has been developed in Europe, in particular in Spain. The design, the engineering, and the construction have been made by a Spanish company, but this solar plant is based in Arizona, in the desert of Arizona, in the United States. It's produced electricity for 70,000 whole houses. If we were talking in Europe, it will produce double for a double of whole house. And it will prevent 500,000 tons of CO2. This plant in Solana has been operated for the last year, and it has a government grant for the United States government, a guarantee for $1.4 million. But what is the solar thermal electricity technology? How it works? What you can see here in your right top, there are two main commercial technologies. What is trough, what is in the top, and down is the tower, with a central receiver with thousands of mirrors, thousands of heliostats, concentrating the energy into the top of the tower. How it works? You have the solar here go through the mirrors, reflect, and concentrate into a tower, which is the solar receiver. In the solar receiver, you will warm it up a heat transfer fluid. With this fluid, we will transfer the heat for the sun to the power cycle. After the solar receiver, what you have is a very conventional power system, but instead of having a combustion with coal, we have a solar field in order to warm it up the fluid. We have also the cooling system and the control system as normal as a very conventional power plant. Let's say what are the set plan strategic objectives for the set plan technology. The set plan has this technology to contribute in 3% of European electricity supply by 2020. With a potential of at least 10% by 2030. The last number that I have found in Eurostat was for 2012, where the contribution of total solar of electricity was 2.2%. I say total because that was the sum for PV plus CSP. So we can imagine we have a great challenge in front of us in order to fulfill those targets. What we can see here in this graph are the megawatt installed today worldwide. We have more than 4,000 megawatt installed in the world. Till 2012, the gain was ruled by Europe and in manner by the United States. Up 2012, China takes the lead, and you can see the other graphic, and other countries awake. Spain, and out of these 4 gigawatt installed worldwide, Spain count of almost a half of 2,000 megawatt installed. Thank you to the Spanish revolution, I will say, from this technology. Europe is today home of the world's leader CSP company. I'm not talking only about the construction. We have the best research center, bank, investor, law officer. The whole sector is leading this type of technology in the world. And that was thank you because Spanish have led this revolution. Out of these 25 gigawatt that are under development, almost like more than 19% will be developed out of Europe. But anyways, most of their technology still come from Europe, thanks to the innovative edge European company has gained in Spain. To keep this leadership, we need to develop, we need to continue with European, domestic products. We need to have a domestic market. The International Energy Agency had forecast that Europe needs to have 15 gigabytes by 2013. So we need to keep this leadership in technology. Out of these 4 gigabytes, what Abengoa has built in the world, being the main player in this technology in the world, is more than 2,000, split in Europe, in particular in Spain, but also Middle East, Africa, Chile, South Africa, and also in the United States. You can see here how many megabytes we have installed worldwide. Continue with the integrated roadmap and the guideline of the set plan had set 4 main targets for this technology. I will go one by one. The first one is increase efficiency and reduce the generation cost. How we increase efficiency? What you see here is the picture. This is a fabulous revolution because that's happened since 2007. The first plan here, what is called PS10, was based in Spain, and it's the first commercial plan of this technology. It has 10 megabytes, and it has saturated steam. That means we have 260 degrees in the receiver. So in the receiver, where the sunlight is concentrated, we have 260 degrees. That is telling you the efficiency that you're going to have in the turbine, because this is the temperature that goes in the turbine. So it's telling you what is the efficiency. The next step was to have superheated steam, and you can see in the next column where we reach 530. 260, 530 in 3 years. So that's double, almost double the efficiency of this technology. This plant, that is the second one here, is under construction in South Africa right now. The third step was, instead of having steam heat transfer fluid, so we changed it for molten salt. We are increasing the energy intensity of the fluid, so we can have more energy in less volume. So then we reach 565 degrees in this third plant, which is under construction in Chile right now. Then you can see with this plan we are reaching the efficiency. What you can see in the last column, the two last one, the gray one, are the conventional power plants. So we are already reaching the efficiency of the best coal combined, the best coal power plant. But we go further. The last picture here, the small one, is a pilot plant facility based in our research center in Sevilla, where we are testing air as heat transfer fluid. So no steam, no molten salt, we're testing compressed air. So we can go to a gas turbine. Gas turbine reaching more than 50% of efficiency. So we are reaching here 1,000 degrees in the receiver. So you can see in 7 years, we increased the efficiency 75% of this technology. Also talking about the generation cost, this is the forecast of the International Energy Agency for the reducing the cost generation. The research objectives for this technology are cheaper and more efficient solar field. When you can see these 2 pictures here, the second and the third, we light the solar field. We reduce the weight of the heliostat and the structure. Also, we have to increase the receiver efficiency, what is the first picture here and the last 2. Higher temperature, higher pressure of the heat transfer fluid, but also in the turbine, and testing new cycle for the power cycle. Other opportunities are also for cost reduction, include supply chain and scale, and follow the learning curves. The second target of the integrated set plan is the improvement on the operational flexibility and energy dispatchability. CSP plant can store as part of the sun that they harvest during the day in thermal energy that can be delivered adapting to the demand needs. That is, we can deliver energy out of the solar radiation. That's what you can see in the other picture right there. That is a normal day in Arizona, where the black line is the demand. where the blue line is the solar radiation, and the green line is how our plant is producing, adapting to the demand, and not adapting to the solar radiation. That's why we are dispatchable. That is a great difference between this technology and the other intermittent renewables technology. So, in fact, this solar technology with the storage can help to integrate the intermittent renewables by providing power on demand, but also ancillary service to the grid. This technology can also be hybridized with other energy sources because, as I told you, we share the power block. So we're sharing the power block so you can drive with solar, but you can also drive with biomass, with coal, with gas, whatever. And that will increase the ability to deliver electricity at any times. In terms of the third target of the set plan, we have the second targets. Here is an example about different concepts of materials for thermal energy storage. What you see here in the top is molten salt storage, then you have a concrete tank for pressurized steam, and down, that is a project that we are driving in Australia, with Zero, that is a research center in Australia, where we are testing aluminum and ceramic storage in order to provide for a supercritical CO2 steam turbine, supercritical CO2 turbine. We will increase the power efficiency, the power system efficiency again. In the other side, what you can see here in yellow is what we have called a concept for the smart solar plant. When we put together concentrated solar power, PV, but also biochemical storage in order to have a faster response. So we produce 24 hours 7, and then we are able to format the grid, to provide faster response to the grid. So all these under the smart control. Wake up. Okay. So now the third improvement of the environmental footprint. That is also a very important point, and I bring you here an example. Usually, those kind of technologies use wet cooling as the thermal conventional power system. But here in South Africa, we were asked to have dry cooling to reduce the water consumption. So we aim to reduce 90% the water consumption in this technology because the dry cooling is not a new technology, but what we have to do here is, like you see, this tower is a big tower because we're using the tower as a chimney in order to have altogether like no natural flow for the dry cooling. So we are reducing the water consumption and reducing the environmental footprint of this technology. Here also some advanced concept and design. As I told you, this here is solo gas, where we are driving to reach 1,000 degrees in the receiver, and we are driving a gas turbine. So we will be competitive in terms of efficiency with the gas turbine. And then on the other side is this one in order to drive a CO2 supercritical turbine. We are reaching high 800 degrees with ceramic and different materials. To conclude, here you can see in the map, the sun has the potential to cover the world electricity demand. What you can see here in the map, this red square is the area that we need in the Sahara Desert in order to produce the electricity demand of the world. So we have the technology, it's there, it's ready, it's green, it's dispatchable, and we have the resource, we have the sun, and it's enough resources to cover the demand in the world. So what we are lack for here, that you can see, are the interconnection. You don't see here any connection between Africa and Europe. So we need to build the interconnection in order to provide solar energy to the north of Europe. Spain is ready to do that, and we're just willing to have more interconnection in order to cover the electricity demand. Thank you very much.
Thank you very much, Dr. Diaz. Thanks first of all for your eloquence. This is a technology maybe not everybody knows in detail, and you really showed us how it works, how on the one hand research contributes a lot to the value chain, and on the other hand how it can be integrated in a flexible energy system. I would emphasize also this flexibility how it can work together with other ways of generating renewable energy. I think it was an excellent example, and it fully fits in the concept of the integrated roadmap. So thanks a lot for it.